How is this working? What can I do? Need an explanation? Then just ask the dudes.
Hello and welcome to our new YouTube video. We did a lot of research and we were looking for the things that people were interested in the most on the internet. And this is how we came to our today's question. Can you shoot a bullet into space? Let's find out. First of all, we need to define what is space and where does it start. Therefore, we have to look at the Earth. As all of us agree, the Earth is not flat. Our Earth is a sphere that's covered by the atmosphere, which you can see in this cartoon right here. And as you already see, the atmosphere is very, very thin compared to the overall size of the Earth. So we need to take a closer look and zoom in. And that's what we will do right here. To better define and characterize the Earth's surrounding gas phase, the atmosphere is divided into several parts. The first part, and the closest to the surface, is the troposphere, which has its range from 0 to 12 kilometers, or 7.456 miles. This is where people go skydiving, where airplanes fly, and where most of our weather phenomena are happening. The second part is the stratosphere, and ranges from 12 kilometers up to 50 kilometers. Here our famous ozone layer is located, and this is also where Felix Baumgartner made his incredible Stratos jump. The next layer, the mesosphere, going from 50 kilometers up to 90 kilometers. If you have ever seen a shooting star in the night sky, this is where it happened. In the mesosphere, usually all of the meteors burn up and make us wish for pretty things that usually never come true. Almost the last layer now, the thermosphere, which ranges from 80 to 700 kilometers. Entering the thermosphere, the density of the air is already 5 magnitudes lower than the density of the air at the closed surface. In this layer, almost all of the satellites are located, and this is also where the International Space Station, or short the ISS, is circling our planet within 1.5 hours. Last but definitely not least, the exosphere, which goes from 700 kilometers up to 10,000 kilometers and is therefore the biggest layer of the atmosphere. But as the name already implies, it's not really a part of the Earth's atmosphere anymore, because it's already too far away and doesn't contribute as much gaseous matter as the other layers do. The density of the air is always decreasing the further away we go from the Earth. At around about 120 kilometers is where the atmosphere starts to have noteworthy effects. Therefore, we don't define space at the beginning of the exosphere, but already at 120 kilometers. Otherwise, we couldn't even say that the ISS is flying through space, and the ISS is even called International Space Station. So it's fair to say that the atmosphere ranges up until 120 kilometers or 74 miles. Now that we define space, we need to have a closer look at our weapons and projectiles. As you can hear, we are not American, but German, and therefore don't really know much about guns and weapons. But after long research on the internet and Wikipedia, we decided to compare these 3 guns. Our first gun, the Heckler&Koch P8 pistol, made in Germany. The AK-P8 shoots 9x19 projectiles. This gun is used by the Bundeswehr. The next weapon we picked is the AK-47 Kalashnikov with 5.45x39 projectiles. This Soviet assault rifle is probably the most famous weapon on the Earth and is used by at least 60 armies. The third weapon we decided to calculate with is the Barrett M82, produced in the United States. It shoots 12 7x99 projectiles and is a caliber 50 weapon. This rifle is used by Germany, Austria, the Czech Republic, India, Malaysia, and of course the US. Now, finally, the calculations. Can you shoot with any of these guns into space? Before we go on, please make sure that you like this video and subscribe to our channel so that we can go on making these science-related videos for you to enjoy. If you already have a question or found something interesting that you want to know more about, leave a comment and ask the dudes. Let's think about what kind of forces act on our bullet. Of course, the projectiles experience accelerating forces from the exploding powder. We mark this force with the arrow going upwards. The second force the bullet experiences, and which slows down its movement, is the gravitation of the Earth. Since weapons are dangerous, we highly recommend to only try shooting at restricted areas where shooting is allowed. Also, we urge you to never try shooting vertically in the air ever in real life, since the bullet is flying down again afterwards and might hurt somebody badly. Okay, we separate our shooting procedure into 3 parts. The first one is where our bullet is still in the gun's magazine. Here the projectile doesn't have any kinetic energy and also doesn't have potential energy yet. As soon as we shoot our bullet, we come to sequence 2, where our bullet has maximum kinetic energy, defined as E equals the half mv squared, where m is the mass and v is the bullet's velocity. The potential energy is still at 0. Followed by this sequence comes part 3, where our bullet reaches its highest altitude, turns around and starts falling back down to the earth again. At this point the kinetic energy is 0 again, because the bullet doesn't move anymore. The potential energy now turned to its maximum, defined as E equals m times g times h, where m is the mass again, g is the gravitational acceleration, and h is the height of the bullet. After sequence 3, the bullet accelerates towards the earth again and hits the ground after a while. To calculate the maximum altitude we reached by shooting into the sky, we take the energy conservation into account. This basically says that all the energy an object contains cannot be lost but only converted into different forms of energy. Therefore, the kinetic energy of the bullet right at the time when we shot it must be equal to the potential energy of the bullet when it reached its highest altitude. So we write mgh equals the half of mv squared. Since the mass appears on both sides of the equation, we can simply cut it out. Rearrange the equation and come to the result of the height of h equals the half of v squared divided by g. Now to the results of this calculation. The values for the exit velocities of the different weapons that we found on the internet are 437 meters per second for the P8, 930 meters per second for the AK-47, and 846 meters per second for the Barrett M82. With a gravitational acceleration of 9.81 meters per square seconds, we come to a result for the P8 of 9,733 meters. For the AK-47, we come to a result of 44,082, and for the Barrett, only 36,522 meters. But something is missing. We forgot something. Right. The atmosphere, or better, the air resistance. So, let's go back to our force diagram and think about it again. Same as before, we have the force on our bullet that comes from the exploding powder. Also again, as always, the gravity works on our bullet. But now, and that's new, the air resistance F is working against our bullet. Therefore we have a second force trying to hold our bullet at the ground. Let's start calculating again. The equation of motion according to Newton's law is F equals the mass times the acceleration. Now it's not only the weight of the bullet that needs to be considered, but also the air resistance that slows down the movement. The air resistance is defined as a force. F of the air resistance equals 1/2 the density of the air times CD times the area that's working against the air times the squared velocity. CD is the resistance coefficient, which is related to the geometry of the body as you can see in this diagram. For the CD factor of the bullet, we always took the value of 0.4. We define a factor C as 1/2 times the density times CD times A, which separates the non-exponential part F equals CV squared. From our force diagram, we can conclude minus G minus F of the air resistance equals M times A. Now we insert for the gravitational force G equals M times G prime and F equals CV squared. Thereby we get minus mg prime minus CV squared equals MA. And further we rearrange to A equals minus G prime minus CV squared times M. Now, the acceleration is no longer constant, but given as a function of the speed. A equals dv divided by dt. However, the speed is not only determined as a function of the time t, but also of the location or height coordinate h. The equation is therefore extended by dh divided by dh. We can also write this as A equals dV divided by dH times dH divided by dt, where dH divided by dt equals the velocity v, where in the end we get A equals dV divided by dH times v. Rearrangement leads to v dV equals A dH. Now, for A we can insert minus g prime minus cv squared times m, and we get v divided by minus g prime minus cv squared divided by m dv equals dH. This further leads to this integral, where we simply have to integrate. To solve this integral, we need some basic mathematical operations. After a substitution with alpha and some conversions follows the re-substitution. In the end, we get this equation, with which we can determine the height of the bullet in consideration with the air resistance. Now we just have to fill in the parameters and calculate the maximum altitudes. If you have any questions up to this point, feel free to leave a comment below and ask the dudes. Either way, if you haven't already, make sure to like this video and subscribe to our channel. But now, let's get to the results. For the calculations, we took the following parameters into our equation. Now, which gun can shoot the highest? And even more important, can it shoot into space? For the Heckler&Koch P8, the final result for the maximum altitude is 829.71 meters. For the AK-47 Kalashnikov, the obtained highest altitude is 1868.97 meters. And for the last rifle, the Barrett M82, we calculated a value H of 2,947.34 meters. So on place 3 we get the P8, second best the AK-47, and the winner of this contest in this comparison is the Barrett M82. But did the Barrett really shoot into space? Let's remember what we learned about the Earth's atmosphere. The closest layer of the atmosphere to the Earth was the troposphere, which ranged from 0 to 12 kilometers. Our highest bullet, the 12.7x99 projectile, reaches up to almost 3 kilometers, which is about this high. So we can conclude that it will probably never be possible to shoot a bullet with a regular pistol or rifle into space. But why did the AK shoot higher in the first calculation, and in the second calculation with the air resistance the Barrett got higher? The simple reason for that is the mass. In the first part, without the air resistance, we calculated the highest point with the help of the energy conservation law, which says G times H equals the half of V squared. When we took the air resistance into account, we no longer could use this law due to the conversion of kinetic energy into other forms of energy than just the potential energy. As you can see in this equation that we used for our calculation, here, here and here we have m for mass, which basically tells us that now not only the exit speed of the bullet is important for the height, but also other parameters, especially the mass. And because the mass of the Barrett projectile is much higher than the mass of the AK projectile, this leads to a higher momentum of the Barrett projectile and thereby in the end a higher possible altitude. So, we came to the end of our video. Thank you very much for watching. If you enjoyed this video or found any information in it interesting or helpful, then please like this video. If you have any further question, if there is anything left unclear or you just want to say some nice words, then please leave a comment below. We are very looking forward to hearing from you. And please, if you want to see more from us and you're interested in science, then please subscribe to our channel. It would mean a lot to us. Thank you very much.